students, myself Dr. Divya, Assistant Professor at Department of Chemistry, Institute of Aeronautical Engineering. Today we will start the next module, Engineering Materials. So the outcomes would be the understanding the classification of polymers with some examples. So here are the topics: Introduction to polymers, then types of polymers depending on their origin, structure, nature of monomers that are used, then intermolecular forces, then based on the synthesis methods. So these are the different types of polymers. So we will see in detail with different examples. So introduction to polymers. So polymers is derived from a Greek word. Poly means many and meros means parts, many parts. So if we see this picture, this is a monomer. So many monomers are joined together to form a polymer. So these large number of small and simple molecules are joined together to get a giant molecule known as macromolecules. So the products containing these macromolecules are known as polymers. So the club of molecules are known as polymers. So the process of joining together of simple molecules is called as polymerization. This is a process that is involving the joining of simple molecules or monomeric units that is called polymerization. So the small molecules composed of at least two kinds of monomeric units. So if we are using two different kinds of monomeric units as a small parts, then it is called as copolymers. So the product formed is called as copolymers. The number of repeating units. So we have many monomers. So these are many monomers that are present in a polymer. So the number of repeating units present in a polymer is called as degree of polymerization. Nothing but it will indicate the polymerization whatever is taking place, and is also known as the degree of polymerization. So the classification of polymers involves based on origin of source. So depending on the source, there are three types: natural polymers, semi-synthetic polymers, and synthetic polymers. So we will go in detail. Then the structure, based on the structure, whether the monomers are depending on the arrangement of monomers, there are linear polymers, branch-chained polymers, and cross-linked polymers. Then depending on the molecular forces, whether they are hydrogen bonding or dipole-dipole interactions or van der Waals forces, it is classified into elastomers, fibers, thermoplastics, and thermosetting polymers. So the method is also very important where the polymerization takes place. So depending on the mode of polymerization, it is addition polymers that are forming and condensation polymers. So these are the basic classification that is for the polymers. So we will go in detail one by one. So based on the origin of a source, there are two types: natural polymers and synthetic polymers. As it is, the name indicates, natural polymers are already occurring in nature. So these are in plants and animals. So examples are proteins, nucleic acids, gums, resins, silk, and natural rubber. So these are the natural polymers that are already present in nature, that is, we are learning from the nature. So this is the protein structure. As we see, there is a simple molecule, and then a secondary structure is forming, and then a helix, tertiary helix, and then the complex structure. So the ultimate structure is a complex molecule that is obtained. So the weight will be very high, like 10,000 to 1 lakh daltons. So the monomers of these proteins are nothing but amino acids. So we have learned in our lower classes that amino acids are the backbones for the proteins. There are different types of amino acids, like 21 different types of amino acids that are linked together to form peptide bonds. So the peptide bond is forming from an amine group of one monomer. So two glycines, when combined together, the hydrogen atom of one amine group, hydroxyl atom from the carboxyl group is joining together to form a peptide bond. So this is how two monomeric units are combined or linked together to form a peptide bond and a protein chain. So these will give us a large variety of proteins. So this is a simple example for our understanding how the natural polymers are formed. So coming to synthetic polymers, these are man-made polymers. Synthetic means man-made polymers. We have a knowledge of natural polymers and we started building up our synthetic polymers for different applications in our daily life. So plastic is the commonly used synthetic polymer. So examples are nylon, polyethylene, PVC, polyvinyl chloride, synthetic rubber, and Teflon. See, these are some of the examples. So, nylon rope. This is a rope that we use in our daily life. Rope is a best example, and some PVC materials in the plumbing and connections that we use. So, how the nylon is forming? From adipic acid, monomeric unit. This is a monomer, and this is a monomer. Monomer 1, monomer 2. So these two are combining together, hexamethylene and adipic acid. So these two are combining together to form nylon. And the polyvinyl chloride, this is the polyvinyl chloride. Upon addition, it forms polyvinyl chloride. So this here, if we observe, the monomers are two different monomers. So these are copolymers forming copolymer. This is the single monomer is used for forming a polymer, so it is a homopolymer. This is also an example of a copolymer and a homopolymer. So these are the synthetic polymers that we are using in our daily life. So based on the structures, there are different reactions that is going on, and the monomeric units tends to form or arrange in different ways. So depending on their arrangement, there are different types of polymers. So linear polymers, branch chain polymers, and cross-linked polymers. So if you see here, the polymer that is forming is linear. So the structure whatever is obtained, the connections of this polymer or the monomers are connected linearly. So the polymers comprising of long straight chains are called linear or straight chain polymers. So the best example is HDP, high density polyethylene. So HDP is the best example that is widely used in bottles and toys. If you see here, bottles where they are having the high strength, and toys that are made from HDPE material. Because these are arranged in a linear fashion, they are closely packed. So they are connected with the backbone carbon. So carbon atoms are used in the connections. So they are closely packed and therefore have high melting points, because it requires high energy for breaking that bond. So therefore, high melting points are present for these materials. So they are used in good applications like bottles, water bottles, and toys. Then based on the structure, the linear polymers are also like branch chain polymers, wherein the chains are having, the linear chains are having branches. So the branch chain molecules cannot pack together because the other group, whatever is forming, has a branch structure. So this branch structure is always lying above this main chain. So they are not closely packed, so therefore have forces that are much weaker when compared to the linear chain polymers. So therefore, highly branched low density polyethylene is flexible. So if we see our previous example, HDPE is strong, has a high strength. However, LDPE, an example for branch chain polymers, have flexible material. They form flexible material. Therefore, they are used in packing films and plastic bags for the grocery. So if you see, they can be molded. If you see this picture, the vegetables are packed very nicely with the low density polyethylene material. So these materials have low melting point due to weak bonding forces. Whenever we see that if we forget our polythene bag near flame, the flame will be attacking, so it burns easily. It means it has weak forces, weak bonding forces. So the polymers that are forming with cross-linking, how do they form? So individual chains are connected. The linear polymers, whatever are there, they are connected with again another chains, linear chains in the forming the networks by covalent bonds. So these are called as cross-linked polymers. These are called cross-linked polymers. These polymers are formed from bifunctional and trifunctional monomers, and the additional functionality is imparted by the cross-links. So this is how the cross-linked polymers happen. And here the best example is the bakelite material that is forming cross-linked polymers. So here the monomers are phenol and formaldehyde. The phenol and formaldehyde, if you see this structure, this is one chain, and this is another chain, second chain. There is one more bond. This is the covalent bond that is forming between these two chains. This is how the network, the cross-linked polymers takes place. So the connections between polymer chains that form the cross-linked polymers or the network strengths can vary. So the strength of these bonds can vary. So strong connections result from chemical bonds. Whenever there is a chemical bonding that is taking place between two chains, it has strong bond or the strength, while weak connections are from hydrogen bonding or van der Waals interactions. So this is how the properties also changes depending on the bonding between these two chains. So one of the example for the cross-linked polymer is the vulcanized synthetic rubber. So this rubber is used in the automobile tires. So if you see this tire, this is tough enough for bearing the wear and strain that is happening during its travel. Another example is the network polymer with weak connections. So weak connection is the jams and jellies. If we see the naturally occurring one, the jams and jellies are has weak connections. Therefore, it forms the jelly-like substance. And the dense network, polymers having dense network, as in bakelite, are very rich and sometimes even brittle. So bakelite is again a good example wherein it forms the dense network of this polymer bonding. So these networks have long and flexible branches. So if there is the branching only a few sides, then it will become rubbery and elastic properties. Just like what we use for the hair bands, it becomes rubbery and elasticity in the polymers if there are only few connections happening at few sides due to this bonding. So tacticity. Tacticity is also very important in polymers, which indicates the arrangement of functional groups. We are saying that depending on the structure, the arrangement of monomers, there are different types of polymers like the long linear chain, branch chain or network. So whenever there is a formation of this network or linear or branch chain, the tacticity comes into the picture, wherein arrangement of these functional groups is also very important. So on the backbone, carbon backbone, polymers is nothing but carbon. So it has all the carbon atoms. The arrangement of functional groups on this carbon backbone is nothing but tacticity. So the practical significance of this tacticity is it varies the physical properties of the polymer. So it indicates the physical properties of that particular polymer. So the regularity of the macromolecular structure influences the rigidity, crystallinity and amorphous order. So there will be some differences in its rigidity, crystallinity and amorphous nature of that polymer depending on the arrangement of functional group. So as we have seen in our lower classes, like depending on the functional group, the reactivity depends. So therefore, when the reactivity varies, the properties also varies. So this knowledge of tacticity also helps in understanding the melting point or the temperature, solubility and mechanical properties. These are the important aspects during our applications to any equipment or the industry. So this tacticity also plays an important role. So depending on the arrangement There are again three types: isotactic polymers, syndiotactic polymers, and atactic polymers. So we will see in detail how these are varying in between. Like if the functional groups are placed on the same side, then it is isotactic. Iso is same. Just remember like this: isotactic. Then syndiotactic, alternating is the syndiotactic. Then atactic, no regularity, no regularity. So there is no regularity, randomly arranged functional groups. So this is atactic. We will see in detail with some examples. The polymers which have the functional groups arranged on the same side are isotactic polymers. Example is polyvinyl chloride. So if you see here, the chloride functional group is placed on single side, one side of that particular carbon chain. So this is an example for isotactic polymers. Then atactic polymers, there is no regular arrangement of functional groups and the backbone of the polymer chain, and these are called as atactic polymers. See, if we see, one functional group is placed here and the second one is alternating here, but however the third one is again placed on the same side, then the fourth one here. So there is no regularity in arrangement of these functional groups. Therefore, it is coming under atactic polymers. So these are formed by the free radical mechanisms such as polyvinyl chloride. So depending on the arrangement also, there is a formation, the mechanism varies. So due to free radical mechanism, the arrangement varied and therefore coming under atactic polymers. So due to their random nature, they are usually amorphous in nature. So examples are polystyrene is a good example of this type. Syndiotactic, the functional groups are arranged in a regular manner on the alternate sides of that carbon chain. So this is nothing but the syndiotactic polymers. These give rise to interpolymer forces of attraction and forms a cohesive system to form a fiber. So this example is the polystyrene made by metallocylene catalysis polymerization with a melting point of 161 degrees centigrade. For the same example, if we see, so these are alternately arranged. For example, if it is arranged on the same side, polystyrene, if we take the same example, if the functional group is arranged on the same side, the melting point is different. So semi-crystalline and it forms slowly, and the melting point is 240 degrees centigrade. And if it is arranged alternately, then it is forming rapidly, still semi-crystalline, but the melting point is 270 degrees centigrade. And if it is atactic, it is amorphous in nature. So this is how the properties also varies for the same material when the arrangement of functional group varies. So then comes the nature of monomers, the monomers that are used in the polymerization reaction. There are two types, homopolymers and copolymers. Homo means what? Same. Homo, same. So polymers which are comprising of one type of monomers are called homopolymers. So if you see this example, if A is a type of monomer, the continuous chain is having only A taken n times. So continuously only one type of monomer is used. Even in this picture, if we see, the blue one is attached continuously, forming a homopolymers. So examples are polyethylene, PVC and nylon 6. These are some of the examples that are forming homopolymers. In our daily life, we use for the textile waterproofing clothing, then bags and strings, yarns for the stitching purposes, then gears, pulleys, bearings and nuts and bolts. See, these are some of the examples that comes under homopolymers used in our daily life. Then polymers comprising of more than one monomer. So if there is different monomers that are used in the polymerization, for example, butadiene and styrene. 1,3-butadiene and styrene are the two monomers that are used, and copolymerization takes place and buna-S is formed. So this comes under copolymers. So buna and nitrile rubber is some of the examples So we are using these for the preparation of footwear and cables and piping, tubings, etc. So these are the best examples for homopolymers and copolymers. Then copolymers are again divided into four types depending on the arrangement of monomeric units. So whenever there are two different monomers, the difference comes like arrangement. So each one has different views, like it has the alternating or the blocking types. So alternate copolymers comes under where polymers comprising alternating units of A and B. So for example, A is one type of monomer and B is another type of monomer. It is alternatively connecting the carbon chain. So this is how it forms the copolymer, and as example is nylon. So these are mostly used in textiles. So these are the good examples, and the block copolymers are forming wherein blocks of A and B are regularly alternating. So the group of friends are again divided into two different groups, and they are forming teams just like that. A is forming a group like block, one block, and another block of B is connected, then again A and B, and the chain goes on increasing. So this is how block copolymers forms. So polystyrene B polymethyl methyl methacrylate is a good example for this type of copolymers. So these are mostly used in furniture, then toys, then trophies that we generally give, then cosmetic boxes, display cases, and then motor lamp, headlamps, and acrylic roof. These are good examples for the block copolymers that are forming. Then graft copolymers, the polymers in which main chain is comprising of one type of monomer and the branches is comprising of different type of monomer. So for example, this is a linear chain that is forming, and the branches are different monomers that are used. So the arrangement is different. So this is how again the graft copolymer grafting is taking place. So graft copolymers are forming. Examples are polystyrene. Polystyrene is a good example for this graft copolymers. So if you see this example, even in the picture, like these are used widely in refrigerating materials during manufacture, then plastic cups, then lighting materials, then sheets, then roofing purpose, helmets, etc. These are some of the good examples that are coming under copolymers of grafting. Then random copolymers. Polymers having no regular arrangement of monomeric units. So these are having no regularity. So they, as they wish, they will be forming together in the monomeric chain. So the the monomers are arranged irregularly arranged. Irregularly arranged. So A, B, A, B. So whatever the reaction takes place, it will be arranged randomly. So the example is styrene butadiene styrene. See, this is a very good example that we use in our footwear, daily footwear, and also automobiles. So here if we see, this is how the red and blue are the two different monomers that are forming or involving in a random copolymerization. So there is no regularity. So this is the styrene unit and the butadiene unit. So in the long way, there is no regularity. The red one indicates the butadiene set and the blue one indicates the styrene unit. So this is how the random copolymer takes place. Then based on intermolecular forces. So whenever there is some reaction going on, there are forces in between two different units, so monomeric units. So based on that, there are four types of polymers. So elastomers in which intermolecular forces are very weak. So elastomers are nothing but rubber-like material. So intermolecular forces are very weak, and these are rubber-like solids with weak interaction forces. And example is rubber. So these are used in the safety shoes, helmets, or plastic bags, and the tires. So these are some of the examples. Then fibers, polymers in which intermolecular forces are very strong. So hydrogen bond or dipole-dipole interactions are called as fibers. So these are strong, tough enough, and have high tensile strength. And examples are nylon and terylene. So the terylene is the one which is used in clothing, and nylon is another best example for the fibers. Then thermoplastics. So the molecules, the monomeric units has different types of interactions. So the polymers in which intermolecular forces are intermediate, they are not strong or they are not weak. So they are thermoplastics. Thermo means heat. So it has some reactivity under heat. These polymers on heating become soft and on cooling becomes hard. So they regain their shape, retain their original shape. So thermoplastics is like they react under heat, they retain their, after cooling, they retain their original shape. So this is purely a physical change and is reversible. So it is retaining back its shape, it means it is reversible and recyclable. It is even recyclable. Examples are polyethylene, polyvinyl chloride, and polystyrene. These are some of the good examples for thermoplastics. So these are used in cables, packing, then pipes, medical catheters, then tensile roofs, flooring, windows, etc. And also toys, centrifuge tubes. So there are wide applications for the PVC and polyethylene. Then comes the thermosettings. Thermosettings, polymers in which extensive cross-linking is present. So the bonding is very close and so called forms the thermosetting plastics. So these polymers are reacting on heat, so they become soft, and on cooling they become hard but do not retain their shape. If we see our daily life also, if there is some burnt switches that are present in the houses, they do not regain its shape. The deformed shape is as such. So it is setting to some shape. On heating, it will be deformed and setting to some shape that is nothing but thermosetting. The crosslinks gets broken and rearranged on heating. The bonds get broken, so they get rearranged to the deformed shape itself. So there is no regaining of that particular shape. Therefore, it's a chemical change and irreversible. And not recyclable also. That is why we use these type of plastics, polymers for longer period usage. So these polymers have improves the material's mechanical properties. So these will improve the mechanical properties of that particular product that is forming out of these polymers. So bakelite is a good example that are used in the switches, knobs. So these are the good examples. And epoxy resins is another example wherein in PCBs we use as a filling agent. Filling for setting the PCB after manufacturing so that the connections do not disturb. So based on the synthesis, the next one is based on synthesis. There are two types like addition and condensation, and depending on the addition reaction, like it is also called as chain polymerization, and condensation reaction, step growth polymerization reaction. So the addition, when we are saying addition also takes place in different ways: free radical addition or ionic and coordination. So when it is ionic, ions always have a cation and anion. So it is cationic and anionic. So these are the different types of reaction that takes place during synthesis, and it varies the properties depending on their reactivity. So addition polymers and condensation polymers. So the polymers which are formed by addition reaction are called as addition polymers. So the best examples are polyethylene, Teflon, and PVC or polyvinyl chloride. So addition polymerization to takes place, the monomer must be unsaturated. For example, A double bond A, or carbon chain. If we consider the carbon chain, it should have some double or triple bonds or multiple bonding. So this is the prerequisite, essential thing for a monomer to have so that it undergoes or participates in the addition polymerization reaction. Then the condensation polymerization. So it is formed wherein condensation reaction takes place. Condensation is giving out some byproducts. So nylon 66 or nylon 6, terylene and bakelite are the examples. examples. And this polymerization, which has the condensation reaction, is called condensation polymerization. These are again three types depending on the byproducts: polyamides, polyesters, and resins. These are the different condensation polymers. So we will see in detail the reaction mechanism in the next session. But just remember that there are three different condensation polymers: polyamides, polyesters, and resins. So what are the differences? So just we'll have a glance what are the differences between addition and condensation polymerization. So if we take the condensation polymerization, it is a step growth. Step by step the polymerization takes place, and in the addition, chain growth. So keep on adding the monomeric units, the chain will be increasing. Then it takes place wherein having reactive functional groups. When we are saying condensation, there is some byproduct forming, so it should be reacting. The functional groups have to be reactive. So in the addition, should have multiple bonds so that it has the lone pair to donate to the new monomeric unit and form the chain. And it takes place with the elimination of simple molecule like water, ammonia, and HCl. So these are the eliminating products, are the molecules that are happening during the polymerization reaction. Then in addition, it takes place without elimination of any simple molecule. We are keeping on adding the monomeric units, so there is no elimination of any products or molecules. Then in condensation, repeating units of monomers are different. So whenever we are using different monomers, the repeating units of the monomers are different. And in addition, repeating units are same. Monomers or units are same. And in condensation, the polymer is formed in gradual steps. So we are, as there is a elimination of some simple molecules, the stepwise growth takes place. So in the addition, the reaction is fast and polymer is forming at once. So we just need unsaturation in the monomeric units. So as such, when we add the monomers together, it reacts fastly and gives the product as such once. So the molecular mass of the polymer increases throughout the reaction. So whenever we are using different monomers, generally the molecular weight increases because of two different monomers. But whereas in addition, we are using only one single monomer, so therefore there is very little change in the molecular mass of that polymer that is formed. Then the product obtained may be thermosetting or thermoplastic. It can give both thermosetting plastics and thermosetting polymers and thermoplastics. Whereas in addition polymerization, it only gives thermoplastics. So that is how the reaction takes place and varies in the properties. The examples are bakelite, polyester, and polyamides. And examples for the addition polymerization are polyethylene, PVC, and polystyrene. So these are the good examples and simple way where we can remember and understand the addition and condensation polymers. So with this, we will see in the next session the reaction mechanism for different polymers that are taking place with good examples. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.